In the final years of the 19th century, humanity believed it was on the verge of knowing everything. The grand clockwork universe, set in motion by Newton, seemed almost completely understood. And the crowning achievement of this era was a set of equations from a Scottish physicist named James Clerk Maxwell. They were beautiful, elegant, and powerful. In just a few lines, Maxwell had unified the seemingly separate forces of electricity and magnetism. And in doing so, he had stumbled upon the true nature of light. His mathematics predicted that a disturbance in an electromagnetic field would travel outwards as a wave. And the speed of this wave was a very specific number. When he calculated it, he found it matched the measured speed of light perfectly. It was a moment of pure triumph. Light was an electromagnetic wave, but this triumph created a profound problem. A crack in the foundations of physics. All waves that humanity had ever known required a medium to travel through. Sound waves travel through air, ocean waves travel through water. Therefore, light waves must be traveling through something too. Scientists gave this mysterious, invisible medium a name, the luminiferous ether. It was imagined to be a massless, frictionless, and completely transparent substance that filled every corner of the universe. It was the silent, unseen ocean upon which the waves of light traveled. The existence of the ether was not a question. It was a logical necessity. The only task left was to prove it was there. The proof should have been simple. The Earth is not stationary. It is hurtling through space, orbiting the sun at 30 kilometers per second. Therefore, it must be moving through the ether, generating a constant ether wind. In 1887, two American scientists, Albert Michelson and Edward Morley, set out to detect this wind. Their experiment was a masterpiece of precision. They built an interferometer, an ingenious device that split a beam of light into two, sent them on perpendicular journeys, and then recombined them. If there was an ether wind, it should slow down the beam traveling against it and speed up the beam traveling with it, causing the two waves to fall out of sync. When recombined, they would create a specific interference pattern, the telltale sign of the ether. Michelson and Morley set up their delicate instrument in a basement, floating it in a pool of mercury to dampen any vibrations. They held their breath and they looked, and they saw nothing. There was no interference pattern. There was no shift. They rotated the apparatus, thinking perhaps the Earth was momentarily stationary against the ether. Still nothing. The result was a catastrophic failure. The experiment that was supposed to confirm the ether had utterly failed to find it. The speed of light was stubbornly, impossibly the same in every direction. It refused to change. It was as if you were running into a headwind, yet the wind had no effect on your speed. It was an answer so absurd, so contrary to all logic and common sense, that it would take another 2 decades for a mind to emerge that was brave enough, or perhaps foolish enough, to not try to explain the result, but to accept it as the truth. The impossible result of the Michelson-Morley experiment left physics in a state of crisis. For nearly 20 years, the greatest scientific minds tried to save the ether, proposing ever more elaborate and contrived explanations. Perhaps the Earth dragged the ether along with it. Perhaps measuring rods physically compressed when moving into the ether wind, perfectly masking the effect. The solutions were becoming more complicated than the problem itself. The truth, when it came, did not come from a grand university laboratory or a famous professor. It came from the mind of a 26-year-old patent clerk in Bern, Switzerland. His name was Albert Einstein, and in 1905, while working his quiet day job, he was about to detonate a bomb under the whole of classical physics. Einstein was not a member of the scientific establishment. He was an outsider, a young man who had struggled to find an academic position, a mind that was free from the ingrained dogmas of the time. He was haunted by a paradox he had been pondering since he was a teenager. What would you see if you could ride alongside a beam of light? According to Maxwell's equations, light was a wave of oscillating electric and magnetic fields. But if you were traveling at the same speed as the wave, it should appear to you as a stationary, frozen wave, a static ripple of electromagnetism fixed in space. Such a thing had never been observed, and Einstein's intuition told him it was a physical impossibility, a violation of Maxwell's own equations. The null result of the Michelson-Morley experiment was not, for Einstein, a problem to be explained away. It was a clue, a fundamental statement about the nature of reality. He decided to take it at face value, to elevate it from a curious experimental finding to a sacred, unbreakable principle. He proposed 2 simple postulates. First, the laws of physics are the same for all observers in uniform motion. Second, the speed of light in a vacuum is the same for all observers, regardless of their own motion or the motion of the light source. The second postulate was an act of pure intellectual heresy. It was a direct acceptance of the absurdity that Michelson and Morley had found. It meant that if someone is flying towards you in a spaceship at half the speed of light and turns on their headlights, the light from those headlights will still approach you at exactly the speed of light, not 1.5 times the speed of light. From these two simple, seemingly contradictory ideas, Einstein began to logically unwind the universe. If the speed of light is absolute, then something else must be relative. Something that everyone had always assumed was absolute, universal, and unchanging. To make the math work, to preserve this one constant speed for every observer in the universe, the very concepts of space and time had to become flexible. They had to stretch and shrink depending on your motion. In a series of papers written in his spare time, in what would become known as his miracle year, Einstein laid out his theory of special relativity. The act ended not with a complex experiment, but with a stunning, paradigm-shattering revelation born from pure thought. The speed of light wasn't just a property of a wave in a non-existent ether. It was something far more fundamental. It was a law of nature so powerful and so absolute that reality itself would bend to protect it. And the first casualty of this new law was time itself. Einstein's solution was elegant, but its consequences were a direct assault on all of human experience. In order to keep the speed of light constant for everyone, his theory demanded that the universe behave in ways that are bizarre, counterintuitive, and a complete shattering of common sense. The first and most profound casualty was the idea of a universal now. For all of history, we have operated on the assumption that time is a great cosmic clock, ticking at the same rate for everyone, everywhere. It is the ultimate metronome, marching forward, absolute and unchanging. Einstein's theory destroyed this clock. It revealed that there is no single, shared present moment across the universe. The very concept of simultaneity, of two events happening at the same time, is a fiction. To understand why, imagine a long, fast-moving train. A person is standing in the exact middle of a carriage. At the very same instant, lightning strikes the front and the back of the train car. For the person on the train, the light from both strikes travels the same distance to their eyes, and they see the flashes simultaneously. They would rightly conclude the strikes happened at the same time, but now consider someone standing on the ground, watching the train speed past. From their perspective, the train is moving forward. The light from the rear strike has to travel farther to catch up to their eyes, while the light from the front strike has a shorter distance to cover, because the train is moving towards it. Therefore, the observer on the ground sees the lightning hit the front of the train before it hits the back. Two events that were simultaneous for one person are not simultaneous for another. The only question that makes sense is, who is right? And Einstein's revolutionary answer is, both of them. There is no absolute truth about which event happened first. Reality itself is relative, depending entirely on your frame of reference. This is the death of now. There is no universal present moment that we all share. Your now is different from the now of someone flying in a jet plane, which is different from the now of an astronaut on the International Space Station, and profoundly different from the now of a galaxy billions of light years away. The universe is not a book where we are all on the same page. It is a collection of countless individual stories, all progressing at their own rates. This shattering of simultaneity gives rise to the most famous consequence of relativity, time dilation. Because the speed of light is constant, if you are moving through space, your time must slow down to compensate. This isn't a mechanical trick or an illusion of perception. Moving clocks literally tick slower. The biological processes of a moving astronaut, the decay of a particle in a high-speed accelerator, the very flow of time in their frame of reference, genuinely slows down relative to a stationary observer. At the same time, space itself warps. An object moving at high speed appears to contract in the direction of its motion. This is length contraction. Both of these effects, time dilation and length contraction, are the universe's way of conspiring to ensure that no matter how you measure it, a beam of light will always pass you at the exact same speed. It is the first terrifying implication of the cosmic speed limit, to protect C. Reality itself must become a fluid, malleable, and deeply personal experience. The shattering of space and time was just the beginning. The cosmic speed limit had another, even more powerful consequence, one that would unlock the deepest secrets of matter and energy. It answers a fundamental question. If you keep pushing an object, giving it more and more energy, why can't it just keep accelerating past the speed of light? The answer lies in what happens to that energy. In our everyday world, when we push something, the energy of our push, the kinetic energy, goes almost entirely into making it move faster. But as an object approaches the speed of light, something strange begins to happen. The universe starts to resist. The object gets harder and harder to accelerate. It's as if it is becoming heavier, its inertia increasing with its speed. Einstein realized that the energy you are pumping into the object is not just increasing its velocity anymore. It is being converted into mass. The object is literally getting more massive as it gets faster. This is not a familiar concept. We think of mass as a fixed intrinsic property of an object. A kilogram is a kilogram. But in Einstein's universe, mass and energy are not separate things. They are two faces of the same coin, interchangeable currencies of the cosmos. The exchange rate between them is the speed of light, squared. This revelation was captured in what would become the most famous equation in the history of science: E equals mc squared. This equation is not just a formula. It is the gatekeeper of the cosmic speed limit. It explains why no object with mass can ever reach the speed of light. As you approach c, your mass begins to increase exponentially. To go just a little bit faster requires a colossal amount of energy. To actually reach the speed of light, your mass would have to become infinite. And to make an object with infinite mass move, you would need an infinite amount of energy. It is a paradox of diminishing returns, a wall of infinite energy that stands between any material object and the ultimate speed. The speed of light is not just a limit. It is an asymptote, a horizon you can approach forever, but never, ever reach. The laws of mass and energy themselves form an unbreakable barrier. But EIMC2 is a two-way street. If energy can be converted into mass, then mass can also be converted into energy. And because the conversion factor, the speed of light squared, is such an astronomically huge number, it means that a tiny, almost insignificant amount of mass can be transformed into a terrifying, world-shattering amount of energy. A single gram of matter, if fully converted, would release the energy of a nuclear bomb. This equation revealed that every object in the universe, every rock, every piece of paper, your own body, is a vessel of unimaginable condensed energy. It is frozen energy, locked away behind the stability of its mass. The speed of light, this simple, constant number, was now revealed to be the key that governs the relationship between existence and energy. It is the reason the stars shine, the source of the sun's power, and the terrifying secret sleeping within the heart of every atom. The cosmic speed limit doesn't just prevent you from going too fast, it dictates the very nature of matter itself. Einstein's theory of special relativity was a revolution, but it was incomplete. It described a universe where space and time were fluid, but it did so only for objects moving at a constant speed, in a straight line. It didn't include the messiness of the real universe, acceleration, gravity, and it explained what happened. Time dilates, length contracts, mass increases, but it didn't offer a deeper, more intuitive reason why. Why is the universe built this way? The next leap in understanding would come not from Einstein himself, but from his former mathematics professor, a man named Hermann Minkowski. He had once called the young Einstein a lazy dog for skipping his lectures. But in 1908, after studying his former student's work, Minkowski was ready to give the theory a new, profound, and geometric foundation. In a now famous lecture, Minkowski stood before an assembly of scientists and made a bold, poetic declaration. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. He had realized that space and time were not separate arenas. They were inextricably woven together into a single four-dimensional continuum. He called it spacetime. This was not just a clever mathematical trick. It was a new vision of the fundamental stage on which reality plays out. Every event in the universe, from the flicker of a candle to the explosion of a supernova, could be plotted as a single point in this four-dimensional fabric, with 3 coordinates for space and 1 for time. In this new picture, the speed of light takes on a completely new and deeper meaning. It is no longer just a speed, a rate of travel through space. It is a fundamental geometric property of space-time itself. It is the conversion factor between the dimensions of space and the dimension of time. The constant c is what stitches the fabric of reality together. It is the one true invariant quantity in spacetime. Just as the Pythagorean theorem defines an unchanging distance between 2 points in space, the geometry of spacetime defines an unchanging interval between 2 events, and this interval is calculated using the speed of light. The reason the speed of light is constant for all observers is because it is woven into the very geometry of the universe. Everyone measures c to be the same for the same reason that everyone agrees that there are 360 degrees in a circle. It is a fundamental definitional truth of the system. This geometric view provides the why. Time dilates and space contracts for a moving observer for the same reason a tilted ruler appears shorter than a ruler held straight. It's a matter of perspective, a projection. When you are standing still, you are viewing space-time from one angle. When you are moving, you are viewing it from a different, rotated angle in this four-dimensional geometry. Your measurements of space and time change, but the underlying space-time interval between events remains the same for everyone. The speed of light is the bedrock of this geometry. It is the cosmic speed limit because it is the fundamental ratio of space to time that defines the shape of our reality. It's not that nothing can travel faster than light. It's that the concept of faster than light is geometrically meaningless in space-time, like asking for a direction that is more north than north. The concept of a unified space-time fabric leads to one of the most elegant and mind-bending ideas in all of physics. It completely reframes our understanding of motion. In our everyday experience, we think of motion as something we choose to do. We can be at rest, or we can be moving. But in the four-dimensional world of space-time, there is no such thing as being at rest. Everything in the universe, from a sleeping cat to a speeding rocket, is constantly in motion. In fact, everything is moving at the exact same speed, all the time. The one true cosmic speed, the speed of light. Think of it like a cosmic speedometer, permanently welded to the dashboard of your existence, and its needle is always, unshakably, pointing at C. This seems impossible. How can you be moving at the speed of light when you are sitting still? The answer lies in the four dimensions of space-time. Your total motion is distributed, or shared, between the three dimensions of space and the one dimension of time. When you are at rest in space, sitting in a chair, for example, you are not moving through the spatial dimensions. Therefore, your entire allotment of motion, the full speed of light, is dedicated to traveling through the dimension of time. This is the fastest that time can possibly flow for you. You are aging at the maximum possible rate. Your personal clock is ticking as fast as the universe allows. The moment you start to move through space, you have to borrow some of that speed from the time dimension. Your speedometer needle is fixed at C. So to increase your speed through space, you must decrease your speed through time. The faster you travel through the spatial dimensions, the slower you must travel through the temporal one. This is time dilation, explained from a new, profound perspective. It's not that your clock is mechanically slowing down. It's that you are literally moving through time more slowly, because you are using more of your fixed cosmic velocity to move through space. If you could, hypothetically, accelerate all the way to the speed of light through space, your speedometer would dedicate all of its motion to the spatial dimensions. There would be no speed left for the time dimension. You would cease to move through time altogether. For you, time would stop. This is precisely the case for light itself. A photon, a particle of light, has no mass. Because of this, it is free to travel only through the spatial dimensions. Its cosmic speedometer is pointed entirely at its motion through space. It has no speed left for the time dimension. From a photon's own point of view, its journey is instantaneous. A photon that leaves a distant star and travels for 1 billion years before hitting your eye experiences no time at all. For the photon, its emission and its absorption happen in the same moment. This reframes the speed of light entirely. It is not just a limit. It is the one true speed of everything. It is the speed of causality itself, the rate at which cause and effect can propagate through the space-time fabric. We are all just surfers on the waves of space-time, and the speed of that wave is, and always will be, c. Today, we see Einstein as a titan, a secular saint of science whose name is synonymous with genius. But in the years following 1905, the scientific establishment saw him very differently. They saw a heretic. The world of physics at the turn of the 20th century was a world built by experimentalists, men who trusted tangible results from their laboratories, men who believed in a mechanical, clockwork universe they could measure and touch. Einstein's theories were not born from a laboratory. They were born from pure thought, from thought experiments, Gedanken experiments, conducted inside his own mind. His conclusions were not just radical. They felt like a philosophical attack on the very nature of reality. The resistance was fierce and deeply personal. Many of the leading physicists of the era simply refused to engage with relativity. They considered it a mathematical fantasy, a bizarre and unnecessary complication with no connection to the real world. They called it cubist physics, a pejorative jab suggesting it was as abstract and divorced from reality as the modern art movements of the time. The idea that time could slow down, that an object's length could contract, that now was not a universal concept. These were not treated as scientific predictions, but as absurdities. The theory was seen as a symptom of a deeper sickness, a move away from the solid ground of experimental fact into the murky waters of abstract speculation. Einstein's struggle for acceptance was a lonely one. For years, he remained at the patent office, his revolutionary papers largely ignored by the very people he hoped to engage. He was an outsider, and the establishment was closing ranks against his strange new ideas. Even Max Planck, the brilliant physicist who was one of the first to recognize the importance of Einstein's work, was hesitant. He accepted the mathematics of relativity, but was deeply uncomfortable with its philosophical implications, initially hoping to retain some form of the old, absolute time. The resistance was a human drama of intellectual inertia. It is one of the hardest things in the world to discard a lifetime of experience, to accept that your own intuition about the nature of reality is fundamentally wrong. Vindication, when it came, did not come from a single grand experiment. It came in trickles from the strange new world of particle physics. In 1938, physicists studying cosmic rays, high-energy particles raining down from space, observed a particle called a muon. Muons are unstable. They have a very short, known lifespan, decaying in just over 2 microseconds. Traveling at nearly the speed of light, they should only be able to travel a few hundred meters before disintegrating. Yet, they were being detected on the surface of the Earth after traveling through many kilometers of atmosphere. The only possible explanation was that, from our point of view on the ground, their internal clocks were ticking incredibly slowly. Time dilation was not a mathematical fantasy. It was a physical reality, being demonstrated every day in the skies above our heads. The resistance began to crumble, not because the old guard had a change of heart, but because a new generation of physicists was encountering the bizarre consequences of relativity firsthand in their particle accelerators and cloud chambers. The lazy dog from the patent office had been right all along. The vindication of relativity was a triumph of theoretical physics, but it carried within it the seeds of a terrifying transformation. The human drama would soon shift from a struggle for acceptance to a desperate struggle with conscience. At the heart of this new chapter was the equation that had revealed the cosmic speed limit's deepest secret, EMC2. For decades, it remained a piece of theoretical curiosity, a profound statement about the latent energy hidden within matter. It explained how the sun burned and why the stars shone. But it felt remote, a cosmic truth with little bearing on human affairs. That all changed in 1938, with the discovery of nuclear fission in Berlin. Scientists had found a way to break open the atom. And in doing so, they had found the key to unlock the power of c². The news sent a shockwave through the community of physicists, many of whom had fled the rising tide of fascism in Europe. They understood the implications immediately. A chain reaction, using the principles of fission, could convert a small amount of mass into a catastrophic amount of energy. The purely theoretical equation born from a patent clerk's musings on a beam of light was now a practical blueprint for a weapon of unimaginable power. The human drama became one of fear and responsibility. Leo Szilard, the brilliant and prescient physicist who first conceived of the nuclear chain reaction, convinced Albert Einstein, now a world-famous figure, to sign a letter. It was addressed to President Franklin D. Roosevelt, warning him that Nazi Germany might be developing an atomic bomb, and urging the United States to do the same. Einstein, a lifelong pacifist, would later call signing this letter the one great mistake of his life. This set in motion the Manhattan Project, the largest and most secret scientific undertaking in history. It was a project populated by the very minds that had pioneered the new physics. Refugees, geniuses, and young, brilliant scientists, all gathered in the remote desert of Los Alamos. Their story is one of the most profound human dramas of the 20th century. Led by the enigmatic and ambitious J. Robert Oppenheimer, they worked with a frantic urgency, driven by the fear that their enemies would succeed first. They were in a race against time, wrestling with the most advanced concepts in the universe while living in a makeshift town, their lives shrouded in secrecy. The moral weight of their task was immense. They were scientists, driven by curiosity and a desire to understand the universe. Yet, they were now tasked with creating a weapon of mass death. They were taking the most elegant and beautiful truths of relativity, the unity of mass and energy, the cosmic speed limit that enforced it, and turning them into a fire that could consume cities. On July 16, 1945, in the New Mexico desert, they tested their creation. As the first atomic fireball lit up the pre-dawn sky, Oppenheimer famously recalled a line from the Bhagavad Gita: "Now I am become death, the destroyer of worlds." The human drama had reached its terrifying climax. The abstract wonder of chasing a light beam had led, step by logical step, to the raw, terrifying power of a man-made star on Earth. The speed of light was not just a cosmic limit, It was the measure of the terrifying power that humanity had, for the first time, unleashed upon itself. The speed of light is an absolute law. In the fabric of space-time, nothing can locally travel faster than a photon. The barrier of infinite mass and energy, policed by EEMC2, is unbreakable. But for as long as humanity has known about this cosmic prison, we have dreamed of finding a loophole. If you can't break the law, perhaps you can bend it. This has led physicists on a hunt for cosmic shortcuts, theoretical possibilities that might allow for faster-than-light, or FTL, travel, not by accelerating a ship beyond sea, but by manipulating the very geometry of spacetime itself. It is a search for a way to cheat the universe's speed limit. The first and most famous of these theoretical loopholes is the wormhole, more formally known as an Einstein-Rosen bridge. The idea grows directly out of Einstein's own theory of general relativity, which describes how mass and energy warp the fabric of spacetime. An extremely dense and massive object like a black hole creates a deep well in spacetime. A wormhole is a hypothetical topological feature, a tunnel that connects two distant points in spacetime. Imagine spacetime as a large sheet of paper. To get from one side to the other, you have to travel a long way across the surface. But what if you could fold the paper over and punch a hole directly through it, connecting the 2 points? You would have created a shortcut. You wouldn't have traveled faster than light across the paper. You would have left the paper entirely, taking a path through a higher dimension. This is the promise of a wormhole. A spaceship could enter one end in our solar system and emerge, moments later, in a distant galaxy. The ship itself would never have broken the local speed limit during its journey through the tunnel. But from the perspective of an outside observer, it would have completed a journey of millions of light years in an impossibly short time. The hunt for a wormhole, however, quickly runs into a colossal problem. According to the mathematics, any wormhole large enough for a person to travel through and stable enough to not instantly collapse would require a special ingredient to prop it open. It would need a substance with properties that defy known physics: exotic matter. This is not dark matter or antimatter. This is matter that has a negative energy density. It would possess a kind of anti-gravity, pushing space-time apart rather than pulling it together. We have never observed such a substance, and we have no idea if it can even exist. A similar requirement plagues the other great dream of FTL travel: the Alcubierre warp drive. Conceived by physicist Miguel Alcubierre in 1994, it is another idea that works within the laws of general relativity. The warp drive would work by creating a bubble of space-time around a spaceship. In front of the bubble, space-time would be compressed, and behind it, space-time would be expanded. The ship itself would be at rest inside this bubble, floating in a calm, flat region of space-time, like a surfer on a wave. But the wave itself, this disturbance in space-time, could be made to travel at any arbitrary speed, potentially many times faster than light. Again, the ship isn't locally breaking the light barrier. It's the road itself that is moving. But just like the wormhole, the Alcubierre drive requires a ring of that same impossible ingredient: exotic matter with negative energy. The hunt for a cosmic shortcut has become a hunt for a substance that may only exist on the chalkboards of theoretical physicists. The loopholes are there, in the equations, but the key to unlocking them remains, for now, a complete mystery. While some physicists hunt for loopholes in the grand, cosmic geometry of relativity, another group is exploring a potential shortcut in a different, far stranger realm: the world of quantum mechanics. Here, in the subatomic domain of particles and probabilities, the rules of our everyday world break down completely. And at the heart of this strangeness is a phenomenon so bizarre that it deeply troubled Einstein himself. He famously called it spooky action at a distance. Today, we call it quantum entanglement, and it represents what might be the most profound and mysterious connection in the entire universe, one that seems to operate without any regard for the cosmic speed limit. Entanglement occurs when two or more quantum particles, like electrons or photons, are linked in such a way that they share the same fate, their properties becoming inextricably correlated. Imagine you have two coins that are quantumly entangled. You give one to a friend who travels to the other side of the galaxy. You flip your coin and it lands on heads. At that exact instant, you know with absolute certainty that your friend's coin, billions of light years away, has landed on tails. The act of measuring your particle has instantly influenced its entangled partner. This connection is immediate. It is not a signal that travels from one particle to the other at the speed of light. It is an instantaneous, non-local connection that seems to violate the very principle that nothing can travel faster than c. This spooky link appeared to be a genuine loophole, a way to send information faster than light. If you could somehow manipulate your particle here to force a specific outcome, you could transmit a message, a series of ones and zeros, to the distant particle instantly. You could have a real-time conversation with someone in the Andromeda galaxy. For decades, this possibility fueled a deep debate in physics. Was the connection real? Or was there some hidden information, some local realism, that the particles carried with them from the start, like two gloves separated into boxes? The outcome would be correlated, but nothing spooky would be happening. In the 1960s, a physicist named John Bell devised a brilliant mathematical theorem, a test that could distinguish between Einstein's preferred hidden information idea and the truly spooky nature of quantum mechanics. Beginning in the 1980s with the work of Alain Aspect and continuing with ever more precise experiments to this day, the results have come back again and again. And they are unambiguous. Einstein was wrong. The spookiness is real. The universe is fundamentally non-local. The connection between entangled particles is instantaneous. The hunt for a loophole seemed to have found its prize, but there is a subtle and frustrating catch. While the connection is real and instantaneous, it turns out to be utterly useless for sending information. The problem is the inherent randomness of quantum mechanics. You cannot force your entangled particle into a specific state. You can only measure it, and the outcome, heads or tails, is completely random. Your friend on the other side of the galaxy will see their particle instantly snap to the opposite state. But the sequence of states they see will also be completely random. There is no way to encode a message in this randomness. To know that a message has even been sent, your friend would have to travel back to you at sublight speeds and compare their random sequence of results with yours. The spooky connection is real, but it is a private, one-way conversation between particles, one that we can listen in on, but can never control. The cosmic speed limit, it seems, has a subtle and powerful defender. Even when reality itself seems to break the rule, it conspires to ensure that no meaningful information ever can. The prison of light holds firm. The cosmic speed limit is more than just a law of physics. It is a fundamental boundary condition for our existence. As we have hunted for loopholes and found them tantalizingly out of reach, we are forced to confront the profound philosophical implications of living in a universe with a hardwired speed limit. The universe is almost incomprehensibly vast, with 2 trillion galaxies stretching across billions of light years. But the constancy of c transforms this vastness into something functionally infinite. It means that, for all practical purposes, we are trapped. The speed of light imposes upon us what can only be described as a cosmic quarantine. It builds the walls of a celestial prison around our solar system, or at best, our local stellar neighborhood. This realization is a humbling and deeply isolating one. For centuries, as we looked to the stars, we dreamed of an age of exploration, of starships charting the galaxy, of a future where humanity would spread across the cosmos. But the speed of light stands as a silent, absolute sentinel against these dreams. The nearest star system, Proxima Centauri, is over 4 light-years away. A journey there, traveling at the fastest speeds our current technology can muster, would take tens of thousands of years. Even a hypothetical starship that could travel at a significant fraction of the speed of light would face a journey of decades or centuries to reach just our closest neighbors. A galactic empire, a federation of worlds, seems to be a fantasy, precluded by the fundamental grammar of the universe. This enforced isolation casts one of humanity's greatest questions in a new, stark light: the Fermi paradox. The question, first posed by physicist Enrico Fermi, is simple. If the universe is so vast and so old, filled with countless stars and potentially habitable planets, why have we found no evidence of intelligent alien life? Where is everybody? The speed of light offers a chilling and plausible answer. We are silent and alone, not because there is no one else out there, but because we are all locked in our own individual cosmic prisons. The universe could be teeming with vibrant, intelligent civilizations, each one exploring its own solar system, each one broadcasting its own art and science into the void. But the distances between us are so immense, and the speed at which information can cross those distances is so slow that we may never hear them, and they may never hear us. The speed of light ensures that interstellar conversations are impossible. A simple hello sent to a civilization in the Andromeda galaxy would take over 2.5 million years to arrive, and another 2.5 million years to receive a reply. It is a communication delay so profound that it renders any meaningful dialogue impossible. The cosmos, then, is not a bustling town square, but a collection of isolated islands, each with its own unique inhabitants, forever separated by an uncrossable ocean of spacetime. The great silence we perceive in the universe may not be a sign of emptiness, but a sign of a fundamental, structural loneliness. imposed upon all life by the one law that governs the propagation of everything. It is the ultimate tyranny of distance, enforced by the one constant speed. The cosmic speed limit doesn't just imprison us in space, it imprisons us in time. It dictates the very nature of our knowledge, ensuring that we can never see the universe as it truly is, in a single objective now. When we look out at the night sky, we are not seeing a snapshot of the present. We are looking into the past. The light from the moon is a little over a second old. The light from the sun is 8 minutes old. The light from Proxima Centauri, our nearest stellar neighbor, is from 4 years ago. And the light from the Andromeda Galaxy shows us that galaxy as it was 2.5 million years in the past, when our own ancestors were just beginning their evolutionary journey. The farther we look, the deeper we are looking into time. The universe we observe is a tapestry woven from countless different pasts, a time machine that we can look through but never enter. This fundamental limitation can be seen as a curse. It means our knowledge of the universe will always be incomplete, always delayed. We can never know the true current state of a distant star system. A civilization could rise and fall in a galaxy 1 billion light years away, and we would not know about it for 1 billion years. We are cosmic historians, sifting through ancient photons, forever disconnected from the present moment of the universe we are studying. This creates a kind of epistemological horizon, a boundary not just of distance, but of knowledge. The universe, in its totality, is unknowable to us in real time. We are confined to our local patch of space-time, our own causal patch, the small bubble of reality that we can interact with and know. But is this limitation truly a curse? Or is it perhaps a blessing in disguise? The prison of light forces us to confront our own significance. By making the cosmos functionally inaccessible, it turns our attention back to the here and now. It makes our world, our solar system, the most important place in the universe, because it is the only place we can ever truly know and affect. If we cannot escape to other stars, then we are forced to take care of our own. If we cannot have conversations with alien civilizations, then we are forced to listen more closely to each other. The speed limit prevents us from running away from our own problems, from seeking easy answers in the vastness of space. It binds us to our home. In this view, the cosmic speed limit is not a barrier to our ambition, but a framework for our meaning. It defines our arena. It makes our present moment infinitely precious, because it is the only moment we truly have. It makes our small corner of the universe the center of our story. Not because of cosmic arrogance, but because of physical necessity. The universe is not a boundless playground for us to explore. It is a home with walls. And it is within these walls that we must create our purpose, find our beauty, and build our future. The speed of light, the great separator, is also the great unifier. It binds all of humanity together on a single, tiny, fragile world, hurtling through the darkness. It forces us to be a local species, and in doing so, it gives us a shared destiny. Our story began with a failed experiment, a search for an invisible ocean that wasn't there. It was a moment of profound confusion that revealed a stubborn, impossible truth. The speed of light does not change. From this single, inconvenient fact, the entire world of classical physics was torn down, and a new universe was born from the mind of a young patent clerk. A universe where space and time were no longer absolute, but a fluid, malleable fabric. A universe where mass and energy were two sides of the same coin, their exchange rate governed by that one. Cosmic constant. A universe with a speed limit. We have journeyed through the beautiful and bizarre consequences of this limit. We saw common sense shattered as we witnessed the death of a universal now and the birth of a reality where time itself is personal. We stared into the heart of each MC2, an equation that guards the light-speed barrier with a wall of infinite energy, while simultaneously revealing that all matter is a vessel of unimaginable power. We learned that we are all, always, moving at the speed of light, surfing the four-dimensional waves of space-time, our motion through time trading off against our motion through space. We felt the human drama of this revolution, the lonely struggle for an idea to be heard, and the terrifying burden of seeing that idea transformed into a weapon that could scorch the earth. We have hunted for loopholes in this perfect law, dreaming of cosmic shortcuts through warped space-time and instantaneous connections in the spooky quantum realm. Yet, at every turn, we have found the universe conspiring to protect its most fundamental rule. The speed of light is not merely a suggestion. It is the law. It is the supreme governor, the principle that gives structure and order to causality. It is the reason the universe has a past, a present, and a future. Without it, reality would descend into a chaotic madness where cause and effect have no meaning. To live in a universe with the speed of light is to accept a series of profound truths. It is to accept that we are isolated, quarantined in our small corner of the cosmos. It is to accept that our knowledge of the universe will always be a look into the past. It is to accept that we are fundamentally and forever a local species. But this is not a story of imprisonment. It is a story of definition. The speed of light is not a cage. It is the frame for our masterpiece. It is the rhythm of reality, the tempo that prevents the symphony of the cosmos from descending into noise. It is the ultimate source of structure. By setting a limit, the universe gives us a world to build in, a time to live in, and a home to care for. It is the law that makes our fleeting, local existence precious and infinitely meaningful. The cosmic speed limit is not a barrier to what we can be. It is the very thing that makes us what we are.